At our notes, section 2.1, part 3. Today we're going to be talking about another form of the derivative that we can use. It's called the alternative form. This is going to be used to find the slope of the tangent line to a curve at one point. See, here's the difference. On your homework, we would come up with these formulas for derivatives. Okay, so like we would come up with this or this. These are going to tell us the slope at any point because we could now plug in our x value. If we want to know the slope at 1, we plug in 1. The slope at 2, we plug in 2, etc. But what if they just give us 1 point and we want to find the slope? That's what we're going to be looking at. So this is the formula that we've been using. This is called the limit process. So if it says to use the limit process, too many S's, 2 S's. When they ask us to use the limit process, they're talking about this one. When they say to use the alternative form, then they're talking about this new one here. Here's the way the new one works. If we want to find the slope of the tangent line at just one specific point, like at 2, we do f of x minus f of c. Well, f of c is just going to be the y value for whatever x we're given, all over x minus c. So we're going to be coming back to this. This is an overview of the 3 methods that we can use to estimate or find the exact rate of change. That's also thought of as the derivative or the slope of the tangent line at a given point. Numerically is one way, and this is the least sophisticated way. This is what mathematicians did before they figured out derivatives. So if you're given an x value, all you'd have to do is come up with another x value that is extremely close to the one that you're given. So like if I give you an x value of 2, comma, you would have to find out the y for whatever function I gave you. Then you could do 2.01, comma, and you could find that answer. What would you do after you had these points? Just find the what? Slope, yeah. So once you have these, you would find out the slope, and that's going to give you a pretty nice estimate. This is going to be a fairly close estimate for the derivative at the given x value. But it's not exact. It's just an estimate. An analytical method is the best way. And this is when we use the limit method to find f prime of x. So we can use one of these 2 methods, either this one or the alternative form. When we use these, we're going to find the exact value for the derivative at that specific point. The last way is graphically. The calculator can find derivatives too. If you go to your calculator, if I have a function in there, and then I go to second, trace, calculate, do you see dy dx here? So if I go down to that, number 6, and now I put in a point, I just have some random function in here. If I put in a point like 2, now look what it does. It tells me dy dx. It tells me the slope right there is negative 18 at that point right there. Okay, so that's another way of doing it. Notice this is not exact either. The calculator is really trying to actually measure the slope by finding 2 points. It's kind of like an estimate like that first way, that numerical way. So the dy dx is probably exactly negative 18, but this is just giving us a very close approximation. So we'll be looking at that method too. All right, so let's look at these first 2 problems. It says use the alternative form of the derivative to find the derivative, meaning the slope, at x equals c if it exists. So this is what we're doing. F prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. Before we actually do that though, let's take a look at why this would work. Let's say we have some function here, and here's our point. This is the point c, comma, f of c. So then I have some other point, let's say that it's really close to this one, and it's x, comma, f of x. Well, if I want to find the slope here, I can just do y minus y over x minus x. That would be our slope formula. But what do I want this x value to be equal to in order to find the slope right here at one point? I want my x value from this to really be the same thing as what? C, right? Wouldn't I want x to equal c if I'm trying to find the slope right here at one point? You guys give me a little nod there if you kind of understand, okay? So that's why it's a limit. I can't really let x equal c. Why can't I let x equal c? It'd be 0 on the bottom, right? So I just want it to be infinitely close as possible. All right? So that's the reason why this formula works. So now let's actually do the problem. So if I want to find f prime of 3, I have to do the limit as x approaches 3 of f of x, that was given, minus f of c. Well, right here, this is my c value, and this is my f of c value. So what's going to go here? 10 all over x minus c, and c was 3. So now I try to plug in 3. I get 10 minus 10, that's 0. I plug in 3, I get 0. I get 0 over 0. I have to do some more work. So I'm going to get x squared minus 9 over x minus 3. This is going to factor down, though, into x minus 3, x plus 3. So now these would cancel out. So now I can plug in f prime of 3 is going to equal, plug it in, 3 plus 3 is 6. So that's going to tell me the slope. For this function, there's the slope at 3. Think about what we really just did. This is a parabola. It opens up. Looks like that. At x equals 3, right about here, we just found the slope. Doesn't it look like that's a positive slope and that it's a pretty steep slope? So that makes sense, that answer we have. Okay, so you should look at things like that too. All right, number 2. Here's our function. This is going to be our c. This is going to be our f of c. How would we find this if we were not given that? Yeah, plug in the x, right, back into the function. Do you see how 2 divided by negative 2 is negative 1? Okay, so if it's not given, we can find it. So now to find f prime, that means the derivative at negative 2, I have to do the limit as x approaches negative 2 of f of x minus f of c all over x minus c. I try to plug in my x value. I get 0 over 0, so I have to do more work. What's the more work I should do here? Multiply by x. So I'm going to multiply this by x and this by x. Always multiply out the numerator. Don't multiply out the denominator. So when I do this then, I'm going to get 2x over x. That's just 2 plus x. On the bottom, I'm not going to multiply that out. I try to plug in. If I plug in, I'm going to get, why am I not getting 0 over 0? Oh, it's negative 2, sorry. This should be negative. So if I plug in negative 2, I'm going to get 0 over 0 again. But what can I do here? Yeah, this is x plus 2 right here as well. So I can cancel this out with that. So now what I have is the limit as x approaches negative 2 of 1 over x. And now we just plug it in, and what do we get? Negative 1/2. That's going to be the slope right there. Guys, look at this from a kind of a graphing perspective. 2 over x looks like this. I'm trying to find the slope at negative 1/2, right about there. or I'm sorry, at negative 2. Negative 2 is right about there. Can you see how that slope looks like it's a negative slope? So that makes sense, that answer. All right, example 3. Evaluate f of 3 and f of 3.01 for example 1. So here's example 1. So I already know I'm going to make a table of values. If I plug 3 into this function, we already know it's 10. It was given. Now I have to plug 3.01 into that function. So if I do that, f of 3.01 is going to be 3.01 squared plus 1. So if I do 3.01 squared plus 1, here's what I get, 10.0601. So see, we're talking about this numerical way that we can find slope. So once I have two x's and two y's, I can now just estimate the slope. F prime of 3, now this is going to be approximate because I'm just kind of using another method that's not as exact, is going to be 10.0601 minus 10 over 3.01 minus 3. Well, if I take 10 away there, I'm going to get 0.0601 over, subtracting those, 0.01. What's this if I divide it? Move this over 2, move this over 2. 6.01 is an estimate for the slope. Is that pretty close to the slope that we got? Yeah. Okay, so again, this is just an estimate. If you didn't know calculus, anybody could be taught to find that an estimate for the slope. But with calculus, we can find the exact answer for the slope. All right. Before we go to the next page, let me just show you how we can check this number 2 on the calculator. Okay, so I'm going to put this in, 2 divided by x. I do a zoom 6, zoom standard. Here's the way it looks. Now I want to find the slope. I'm checking my answer. When x is negative 2, what is the slope? So I go to second trace. I don't want to know a value, I want to know the slope. So I go down to number 6. I put in my x value, negative 2, and it tells me that dy dx is negative 0.500001, which is very close to that. So see how you can use this to check your answers. All right, let's go over to the back now. On this page, we're going to be graphing functions. So we're going to be graphing an original function, and then we're also going to graph the derivative of it. So what would the derivative look like? All right, so what we want to do here then, let's make our axes. All right, so how does the graph y equals 5x, how's that look? It's just going to be what? What kind of function is it? It's a line. It has a y-intercept of 0, slope of 5. So I'm going to go up 5 over 1. I'll just connect all of these. Okay, so there's y equals 5x. Now we're going to graph the derivative. Okay, so here's what I have to do. I'm going to make a table of values. So I'm going to test some x's, negative 2, negative 1, 0, 1, 2. If x is negative 2, what is the slope for this function? What's the slope when x is negative 2? 5. What's the slope when x is negative 1? A 0. What's the slope always? 5. Okay? So our new function then is really just going to be these points right here. So at negative 2, we have an answer of 5. At negative 1, it's 5. At 0, it's 5. It's always 5. So this is how the derivative function will look. When we graph f prime of x, we're talking about our new y values are whatever the derivative was for this function. So can you see how we end up just with the function y equals 5? That's the way this looks. Let me show you how to do this on the calculator. That's a pretty easy problem, but let's look at one that's a little more complicated. Go to y equals, we're actually going to just start with this one. 5x, put it in. Go down to y sub 2. Here I typed up the directions how you would do this. Into y sub 2, you're going to go to math. Go to math. Go to inderiv. See it down here, number 8, inderiv. So we're going to go down to inderiv, and we're going to hit enter. And if you have a newer calculator, it's going to look like this. So we're going to put in d dx, x goes in there. Here we have to say what's our function. Well, we put our function into y sub 1. Do you guys remember where to find y sub 1? Vars, y vars, function, y sub 1. And then here we have to say for what x. And we want to do this for all x's because we want it to graph the entire thing. Does anyone have an older calculator and needs help putting it in? Bring yours up here, Gage. Let me show you how to do this. Let me hit graph here on mine and I'll show you what happens. So it's graphing this and then it's graphing the derivative function. All right. So on the older calculators, here's what we have to do. So he has his 5x and he's got the inderiv in. Then you have to put in a comma and you have to put in an x, comma, x. And that's all written up here in the directions. For the older calculator, it's y sub 1, x, comma, x, comma, x. And now when we hit graph, here's going to be the original function. I don't think we need to do a zoom 6. Hold on. We'll do zoom 6 so that we have the right window. So here's the first one, and then here's the derivative. And see how long it takes the calculator to do the derivative, to graph the derivative? That's because it's really calculating what's the slope there, what's the slope there, what's the slope there. So it's having to calculate all that. All right, makes sense? And guys, here's what I do. I just keep that in there like all day long, even when I'm teaching Algebra 2. I just keep this in here if I'm going to be using it later, and I just turn it off. So if I don't want to see the derivative, I'll just turn it off. So let's say I'm in Algebra 2 and I'm just graphing an inverse function. So I just want to see that inverse function, and so now I can just graph that because I have the other derivative turned off. And they'll probably ask, oh, what's that for? And then I'll say, oh, it's a derivative for calculus. Okay, instead of doing number 5 next, I'd like to go down to number 3. So our original function is negative the absolute value of x. See, I'd like you to know how to graph these on your own, but use the calculator to check. How does negative the absolute value of x look? Upside down V is correct. So it's going to look like that. Okay, so we're going to graph the derivative on our own, and then we're going to check it on the calculator. Okay, so what about at negative 2? At negative 2, what's the slope right there? This is just a slanted line. What's the slope? I didn't graph mine real exact, I should have, but is this going uphill or downhill? Uphill, so this is going to be positive 1. So my slope is positive 1. What about at negative 1? What's the slope? Positive 1 again. At 0 we have a sharp turn. When that happens, the slope is actually undefined. At positive 1, what's the slope here? Negative 1. What about at 2? What's the slope? Negative 1, 3, negative 1, dot, 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 right? And up this way, it would be dot, 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 dot. right, so then if I'm graphing this, we're saying everything less than 0 has a value now of 1. What does a value of 1 look like? Y equals 1. What's that look like? Just a horizontal line, isn't it? So my answers, my slopes are all going to be 1. Now here I'm going to have an open dot because it's undefined right there. And then I'm going to have answers of -1. At 0 it's undefined again, but it's going to look like that. Okay, and the reason why is even here at -0.1, that slope is 1. So as close as I can get to 0, the slope was 1, and then it switches to -1. Now, let's say we didn't really understand that. Well, we can check it on our calculator. We can go to Math. So if we go to Math, Num, absolute value of X, and now let's graph it. Oopsie. No, thank you. So I have to insert my negative. Thanks. So here's our original function, and here's the derivative function. It takes it a long time because it's really trying to calculate what are these slopes. I turned it off. I'm like, gosh, it shouldn't take it that long. There we go. So now it's calculating the slope is 1 for all of these, and then it's saying, oh, okay, the slope's -1 for all of these. Make sense? Pretty nice, right? Okay, let's go down to this one now. -x². This is the toughest one because we don't have exact slopes here. So if we're graphing -x², it's going to look something like that. So I can't find exact slopes here. So watch what I do. At -2, this is a fairly large slope, isn't it? It's a positive and it's large. At -1, it's still positive, but it's a little smaller. At 0, my slope is 0. See how right there, if I make that slope, it's 0. At +1, my slope is negative, but it's fairly small negative because it's like about like that. And then at 2, my slope is negative, and that's going to be very steep. So it's going to be a negative large number. Okay, so I have all this information. So how does that relate? Well, at -2, I have to have a positive, fairly large number. At -1, I have to have a positive, but it's kind of smaller number. At 0, I have 0. At 1, I have a negative number, a negative value for my slope, but it's pretty small. And then at 2, I have a negative value, but it's fairly large. Connect those dots. That's an estimate for what the derivative would look like. Now, that one is pretty tough to do at this point. So if we go in here and we just put in our -x² and we leave that in, when we look at this, we can see it looks like that for the original function. It's thinking about the slopes. So do you see how it's an approximation? Our graph is pretty good approximation, right? Okay, any questions over the graphing? Yes, Gage.
So is a large negative number a number closer to 0?
No. When I say that, because I've said negative, I'm saying that this is going to be like -20, whereas this would be -3. So because I'm specifying that it's negative, I'm saying it's a negative, and then I'm saying it's a large value. You see what I mean? All right, anybody else? Questions on that? Okay, guys, so just going back real quick, make sure that you know this formula. This is the new one. You're going to practice this on some problems in your book. That's going to be when they tell you to use the alternative form. If they tell you to use the limit process, they're talking about using this function back here, this method with the delta x. All right, very good. Let's stop there for a while.